Dr. Kathleen Jones from the Jet Propulsion Laboratory, where she's a radar scientist, and her main research is focused on using radar remote sensing for studying natural disasters and monitoring critical infrastructure. Ben Holt is going to be the presenter. Ben is also from NASA JPL. A quick story about Ben. Ben is an oceanographer. Many years ago, when I was in graduate school, I had a position on the radar remote sensing team. Ben and I were actually working on the same data set. He looking at it from an oceanographer's point of view, and I was doing geologic interpretation. Now, when Ben turns on his camera, you'll see that both Ben and I have aged in the same way. Ben, are you out there and ready to give your talk? There he is. Is there a resemblance?
Bald and bearded.
Yeah.
Yeah, it's a long time ago since Judd and I knew each other.
Yes.
And thanks for inviting us to talk today. This is our first shot with the workshop.
So go ahead and start your presentation. You're on.
Thank you. So here's my cover slide, which I mentioned before. And it actually was not bad that Juan went ahead of me because he provided a lot more introduction material regarding the SAR functionality than I have done, than I will be doing. So most of my focus is going to be on using our airborne SAR, which we call, unfortunately, the UAV SAR. It has one of the world's worst acronyms because while the original proposal was to fly this sensor on a large drone, like a Global Hawk, it never has materialized. And so the sensor flies currently on Gulfstream 3s, and which are two. We have two Gulfstream 3s, one based in Palmdale and the other based at the Johnson Space Center in Texas. So it flies about 38,000 feet. So just so it's not we're not a drone. It's an L-band sensor, which is a relatively longer wavelength than most of the SAR sensors in space. Has a good resolution, multiple polarizations, which have been used successfully quite a bit to derive many different channels. Putting together the polarizations, you're able to derive many different kinds of scattering information, which can be very useful. It's designed primarily for interferometric SAR, which is basically used over land to look at deformation from earthquakes is the best example. It has a quite good radiometric calibration. And one thing to notice that I want to point out and I'll talk about is it has a very low noise floor, which is very important for looking at dark radar signatures such as oil. So Kathleen and I were first actually brought together in a way by a program manager that we both shared, who said, why don't you go fly your plane, the UAV SAR over Deepwater Horizon? So we did. For a couple of days, we had the map shows the collection of all the imagery that was obtained, which was mostly along the vegetation, the coastline. And then we had a couple of flights offshore that covered the Deepwater Horizon slick, as shown in the circle at the bottom. And here's some examples of our data. We didn't collect much. We only had a couple passes, really. And we were actually, we had expectations about what we were going to see, but we were actually quite surprised and happy, let's say, about the variability that we were seeing. Normally, we expect a SAR response to be, kind of uniform in darkness. The the oil suppresses the small waves that generate the radar backscatter, and there used to be a conception that there wasn't much information outside of oil spill extent. But as our data shows, and you can see it here actually, if you look at the scale, which is in dB, but don't worry about, just look at the broad range of numbers on the center scales of the two radar images. We have quite a range of data results over this dark area, ranging from, let's say, minus 22 down to 30 in the 30s or 36 even. And so the best validation, shall we say, that we could obtain was from this helicopter and aerial photography that was obtained the same day as our collection. So we were able to sort of pinpoint different features which are pointed out on the slide. So I'll point out in particular the Langmuir cells, which is a upper ocean boundary layer, atmospheric boundary layer effect that is can be widely seen in many situations from a boat or a plane, where there's a setup in the upper ocean of alternating cells of convergence and divergence. So it can accumulate oil or material or slick material of any sort into these convergent zones, which in this case are shown as the darker orange cells. So this indicates that there is a convergence of the spilled oil into these narrow bands. So, and again, there's quite a broad range of radar backscatter throughout this image. So that was a very, very encouraging and rather unexpected, actually. So we put together some papers. We're including in the AGU monograph. Ira included us in his review paper from 2012. And then we also wrote a really great paper with what I think is a great paper with including a grad student who was at Caltech at the time, Brent Minshew. So it was kind of an interesting review process. I'll briefly digress. We had one reviewer, this was in TGARS, one reviewer who said, this can't happen. I don't understand what they're doing. And the other reviewer said, hey, did you ever think about the dielectric problem? So our light bulbs went on and we said, no, we hadn't thought about the dielectric problem, but it's a big factor. So one of the key things, as I mentioned, so the oil smooths out the ocean and reduces the radar backscatter. So the dielectric constant is the response, the electrical response of a material when in this case, a radar is pointed at it. So the ocean has very high dielectric. So lots of energy is returned. It's not transparent. You can't penetrate into the ocean to any means. All the radar energy is scattered back in all the directions. So so the ocean by itself has a very large dielectric. Oil, on the other hand, has a very low dielectric, so very low conductivity. Actually, when it's thin, the oil is only seen, provides, of course, the smoothing of the ocean, but there's no impact from the dielectric itself, and the sheen is too thin to change the dielectric. However, when the oil gets mixed, it becomes an emulsion, which is by definition a mixture of oil and seawater. you've now produced an intermediate or a new dielectric layer through this mixture of oil and seawater. And that also changes the scattering, the radar scattering. And this is pointed out, the impact or the use of dielectric to potentially estimate oil thickness was also referenced for passive radiometry data in several studies, previous studies, in using the same concept as an important factor in determining thickness and variations in the oil. But of course, passive radiometry, which uses similar frequencies, has a coarser resolution. So we're not measuring thickness directly, but the radar backscatter is responding to this new layer, the volumetric fraction within this emulsified oil. So it's a different component. And so we have to understand now not only the radar scattering from the waves themselves, but also the impact of the different conditions and oil properties and so on, and the environmental conditions on the dielectric constant. So I mentioned at the beginning that UAVSAR, our instrument has a very low noise floor, which is shown in that curve on the left. It ranges across a swath, which is 22 kilometers, but in the middle zones, it's quite low. And so what that allows you to do is to provide quantitative data within this low zone that's not available to satellites SARs, because they have a much higher noise floor. And we need to update this table because it's a little out of date. But basically, you can see the UAVSAR has this range from 35 to 53 dB, and all the satellites listed there, including the present one, Sentinel-1, all have a much lower or higher noise floor. So the UAVSAR is able to see this darker zone where lower backscatter, but yet provide quantitative information within this lower radar zone, let's call it. So to move forward, we're taking the approach to simplify the problem in a way to only use one polarization. So we're taking, many studies have used the multiple polarizations which are possible with our instrument plus the different satellite SARs, but all the systems have different configurations, except that they do have what's called a like polarization, which is shown here as VV. So this is a vertical transmit and vertical receive. Some systems have an HH system, horizontal transmit and horizontal receive. But everything's different, but one thing you can say is that they all have a single, at least one like polarization. And that's where you get your best radar response over the ocean, for example. So we're taking the approach to use what we call the damping ratio, which is a contrast in the radar backscatter between the ocean and the oil. As our colleague that I'll show later flips those two and describes it as the contrast ratio, but basically it's the same idea where you're using the differences between the radar response between the ocean and the oil. And from that variation, we hope to use different levels of the damping ratio to provide information on thickness, different ranges of thickness. So as an algorithm approach, you might set up your bimodal, your histogram, and figure out the bimodal schemes. You figure out where the water is, and separate the water from the ocean, or the water from the oil. And then when you get to the damping ratio, we need to figure out the thresholds first between the ocean and the oil, which is a straightforward one. I mean, not straightforward, but that's certainly the first step. And then and then it looks like we will get to the sheen. We can separate sheen and thin oil from the thicker emulsified oil. And then using this, as shown in this third histogram, this broad scale range of information of the slick area, which is where we hope to derive various ranges of thickness. and how the oil, of course, is impacted by the environment and its own heterogeneity and its varying internal properties. So the first thing we did was we began after our Deepwater Horizon work, we began a great collaboration with Norwegian colleagues from the University of the Arctic in Tromsø, and particularly Camilla Brekke. So we undertook a field campaign to participate in the NOFO exercise in 2015, where several types of emulsified oil were released for us and allowed to remain on the surface without being collected. And we also released, plant oil was released as a biogenic slick simulator. So we have multiple types of SAR overflights, including the UAV. Our goal was indicating the various oil water concentrations in the SAR, but result was that very high winds sort of blurred the released oil through the rapid mixing. So we didn't quite get to our main goal, but we had repeat SAR imaging, which I'll show an example of, and a couple buoys were deployed, and we were able to use our results in a drift model. I'll go over these pretty quickly, but here's a time series of selected snapshots from the released oil on the right-hand panels. They go through time about 8 hours, I guess. And you can see the spreading of the oil over time. And actually the plant oil sort of becomes this little circle. It doesn't get spread out like the rest of the released oil and mixed. It ends up sort of where it started as a little circular feature. So that was of interest that was input into this model. The two kinds of buoys that were released were a surface buoy, more like a surface buoy, an ice sphere that could be transported by the wind, moved around by wind drift, and then a buoy that was about a half meter down that was more subject to the current. And you can see the buoys, the surface buoys, forced by the wind, took off to the east, and the at depth buoys remained in this near inertial circulation pattern, closer to the source of the oil releases. Anyway, so I'll go over this quickly. We had a really interesting paper that was we generated with these Norwegian colleagues who took into account the different particle sizes of the spill of the oil and plant oil, and using these drifter buoys, we're able to simulate and compare drifter predicted currents with our measurements of the oil spread over time for both the plant and released oil. And it was quite a good match. So after that, we participated in a campaign with NOAA, primarily at the Taylor site in November 2016. We were sort of a piggyback flight in that campaign, which was designed to identify the sort of a best methods for in situ sampling of oil thickness, and in comparison with the multiple remote sensors. And our first cut at the results showed promising results using the damping ratio, which I'll show in a moment. And then again, we used the time series to investigate a couple other situations where to look at how well the oil stayed in place, how stable it was, and which parts of the oil seep, this released oil, the spilled oil, varied over time. So here's this is probably well-known knowledge. Different types of samplers were used, including a dip plate and a pad, and then Oscar's water sampler, a tube water sampler. We had lots of variations in the oil measurement components. This is an example of our time series through time of the repeat observations, which shows definitely some stability and some changes over time, and including interactions with the local upper surface ocean. We put these into these damping ratio classes, where the redder components indicate what we believe is the thicker oil. And then we also used compared our damping ratio results with both UAV SAR and RadarSat-2 with some higher level polarimetric analysis done by Oscar and Gordon, which showed comparable results. So now, we're involved with a joint, we had a NASA project funded last year, or late 2019, I guess. That's led by Frank Minaldo, who did a lot of work with NOAA, and now he's associated with the University of Maryland. The list of colleagues involved is shown after that, including the cast of characters from Lisa and George Grettinger, Sean Helfrich from NOAA, as well as Ellen and Juan, actually, in this case, is associated, and Oscar Garcia with our collaborators of Gordon Staples, who you'll hear from next. Again, our colleague in Norway, Camilla Brecky, and Dana Toulis has become involved with providing access to a Coast Guard cutter. So the goal is to move a thickness algorithm with SAR-based thickness algorithm into NOAA's operational efforts that Juan described. And the first thing I'll say is that part of this proposal was 3 field tests, two based at Santa Barbara at the natural seeps, and 1 to be in Norway. We've been delayed from COVID, and now we're currently scheduled to have our first field test in May 2021, and a possible second test later that year. This test is currently planned to be on the Coast Guard cutter provided, Blackfin provided, as mentioned organized by Dana Toulis. And then we hope to go back to Norway to participate in another one of these oil and water exercises in June of 2022. And so we will have this coordinated measurements, in situ measurements of oil thickness and type with our plane again, and a collection of satellite sensors that are accessible, particularly through NOAA and everybody. And so the field test will be designed to provide really a broad scale in situ measurements. And we're going to include Oscar's drone collections as well across these slick areas. And we need to obtain, knowledge. We need to have knowledge of the slicks actually ahead of time, not the slick locations, but where the slicks are, because they're highly variable in their drift based on the weather and the wind and currents. And we hope to follow that through time, follow the slicks through time as they evolve and drift. Okay, so I just sort of said that. And again, this is an example of using the damping ratio that we'll be sort of validating now with our field tests to use for providing this indication of varying thicknesses within sentinel images primarily, or SAR satellite-based images. Okay, so provide an overview of our efforts to date. We think we can provide good quantitative oil spill properties. We need to have improved validation with in situ collections. Focuses on using simple parameters that are accessible from all satellite-borne sensors. We, of course, have the false positives to worry about with biogenic films as well as low winds. And here's a different range of thicknesses as we hope to get to. And we're working on a radar scattering model, which I didn't discuss, but to pull all these kind of things together, including oil properties and water concentration to help us predict and derived oil thicknesses and the various sensitivities. And so there was some discussion about sea ice. So we've also sort of published 2 studies separating new young ice from oil using SAR collections of by the same sensors of oil and young ice, but separately. I mean, there hasn't been an oil spill in the Arctic that we know of or we're able to access, but they have very similar signatures. Okay, so thanks.